Alan Irwin here from Santa Barbara Infrared. In this video, we're going to be talking about the modulation transfer function, more commonly known as the MTF measurement. So what is it that MTF measures? MTF measures a camera's spatial resolution. In common terminology, what we do is we measure how small an object a camera can see. And when we talk about size, small and big, what we're really talking about is angular subtense. So in this slide, I try to illustrate that it doesn't really matter the absolute size of an object. It matters how big it appears in the camera. So you can have a person that's up very close, and he can appear larger than a tank that's at a very long distance away. And that's what we mean by size, and we more accurately call it angular subtense. So what affects MTF? How does the MTF change? Well, the MTF, or our ability to see small things, is affected by, one, how the camera is designed. If we have a smaller sensor element and we have really good optics, we can see very small objects. But larger sensor elements and optics that are built for something, we may see only larger objects. It just depends on the manufacturing of the camera. Environmental effects impact us. Are we looking at something in a foggy day, or is it a clear, bright day, or is it underwater? All those environmental effects impact how small an object we can effectively see. And then, is the camera properly focused? And this is a fairly common problem where a camera goes out of focus, and so we're not seeing as well as the system can actually produce, and we need to refocus the camera. That's sort of our calibrated correction. Now this is a typical MTF curve, and what it tells us is how well we can see things relative to each other depending on their size. The way that you interpret this graph is that the bottom axis on the left are big things, and on the right are small things. So that tells us relative size. The vertical axis tells us how well we can see things. Up at the top, where we see 1.0, that's when we can very easily see something, and the farther down we go in that image, the harder it is to see something. So what this graph tells us is that it's easy to see big things, and it's hard to see small things. Of course, the details of the numbers are what give us the really important information, but that's the general interpretation of this graph and what you could expect to see. So when we talk about angular subtense, that bottom axis, we're talking about spatial frequency as the unit of measure. So what is spatial frequency? Well, let's take a look at this slide. We have the same angle on the left and on the right. But on the left, something that's very large, we can only see one of in that angle. But on the right, if we have smaller things, we can fit more of them inside of an angle. And if we think of those things as a spatial frequency, a cycle, then it's only one cycle per, let's say, a milliradian on the left, but it's 4 cycles per milliradian on the right. What that tells us is the larger the number in spatial frequency, the smaller the object. And that is actually the relationship. That's how those numbers are derived. Now this graph, it's actually of the same camera. And on the left, what we see is that the camera shows us that we are not as well focused. We cannot see objects, small objects, as well. We can kind of tell that by just looking at the middle point. That's where the ability to see something is at 0.5. What that roughly means is that 50% of the time you should see something that big, and 50% of the time you won't be able to see something that big. And we can look at the point on the graph and come down and see what that size is. On the right, we have the camera more properly focused. And in this case, we can see a larger spatial frequency or a smaller object. This is in fact the same camera. I just moved it out of focus when I did our 2 measurements so we could see the impact of focus on our graph. So how do we do these measurements? Well, we conduct the measurement using an edge. This is a very common method, the edge methodology, and it's been implemented and improved upon in several ways. In fact, what we're going to talk about is a standard edge method and then the more improved modern edge method that actually, again, has a standard around it. What we do is we look across this edge and we take a reading. So in this actual graph from that reading we saw, we can see the step function. We've gone from bright to dark, and we have that information recorded here as to how well we've made that step. The next thing we do is we take that information, we differentiate the curve, and we produce what's called a line spread function. In other places, it's referred to as an impulse function, if you look at signal theory. And that impulse function, if we had a perfect transfer system, a perfect camera, if we had an impulse coming in, we'd have an impulse coming out. But in fact, although we put an effective impulse in, we differentiate an edge to produce an effective impulse, what comes out is this spread line. And it's that spread that gives us all the information we need about the camera. Because what we're going to do next is a Fourier transform on that impulse response, that line spread function, and produce a graph of relative response based on spatial frequency. We normalize the graph and we look at the power output, so there's a little more math involved, but that's the key component, is we do a Fourier transform, and since this is all digital, it's a fast Fourier transform, the FFT. It's performed on that curve, and we generate this MTF curve. And that's all we need to do around that function. But the actual details of performing the test are as follows. Once again, we come back to needing that black body, a calibrated source so we know the temperature that's put out. What's interesting is that we don't really need such precise calibration on that black body. We just need an effective step. We want the step to be within the linear range, going all the way back to the SITF function. We use that to determine what the temperature is that we want to set. We don't want to saturate the camera. We want to be in the linear range of the camera to produce that curve. So we've got our black body, and then we have our setup. In this case, we have to be in a projected system. So here we have a target projection system, and what we mean by that is that there is a target, that edge that we've seen in other cases. That's where we have a circular area and we're only seeing half that area. That line that divides the left to right half is a very precise edge. We take that and we project it through some optics. Put a black body behind it, we have our target. The target projection system optically projects that to the camera so we can control its size, and we project that to the camera so the camera can then take its measurement. We know all the details of the stimulus, we can look at the details of the response and do our calculations on the system. Some of the detailed information we're interested in is what the temperature is. We're actually going to set the black body out, what's the area that we're going to be using. There are some methods that we can use for dealing with noise, but all that stuff gets set up in advance, and then we run the test, and what we see is that edge. And that's where we're going to go forward with our further analysis of the system. This slide shows one of the issues that we have with MTF. Where does the edge fall on the sensor? When that edge happens to fall perfectly, as in this diagram shows, the edge that's projected falls exactly between two sensor elements along the whole row. We get a perfect step, which is fine. But what if, in this next slide, we show the edge falls halfway along a sensor? Well, we're only going to get half the response from that set of elements. So when we look at the edge, there's this step function. It's nowhere near as precise as a single step. We have these multiple steps, and so we lose information. This is referred to as the phase problem in MTF. Where the line hits, where the edge hits on our sensor impacts the result, the way the results come out and the way we analyze it. So this phase problem needs to be dealt with, because otherwise every time you put the camera back in the system for testing, it's going to be a little bit different. Even if you have an extremely precise way of mounting that camera, you'll have variation. You'll have variation from one camera to the next. So if you're in a production line, they don't all have perfect bolting down in the exact same position. You have variation. You can spend time adjusting it, but there's a better way to approach this problem, and that is with what's referred to as a slanted edge. So the slanted edge MTF method is by far the most common way of doing MTF. And here we can see what a slanted edge looks like. It's basically the edge of a target, only we've got it at a slight slant. Now what we're going to do, and what we'll see in the next slide, is that we have the edge going along the elements where they cross at different places along that sensor element along each row. And what you have are different phases on every line. So if we take each individual line and do an MTF analysis on the line, we get different phase responses. After doing all the analysis, we can average everything in MTF space, and by doing that average, we can eliminate the phase problem by averaging out the phases. So that's one common way of dealing with the phase problem. What it does is doesn't give you the most optimum MTF analysis, but it gives you a consistent MTF analysis so that you can go from one camera to the next, or take the camera off the system, put it back in, and you should reliably get the same MTF result. Okay, there are some problems with this edge method. The first problem is noise. There's that little step where we differentiate the edge. Unfortunately, that tends to heighten noise. It makes the noise much bigger in our line spread function than it was in our edge spread function. The way we traditionally deal with that has to do with averaging frames, all the things we needed to do when we were addressing noise back in our noise video. We can also do some tricks that are involved with pedestal removal and averaging some images. But what's important to know is that we want to reduce that noise, ideally at the source. If we know we have a noise source, we want to try to eliminate it and reduce the noise as much as possible. It does impact the results. The second problem is referred to as aliasing. Now this has to do with the fact that you have a built-in limit in your camera on how small a thing you can see. It has to do with the geometry of the system, the size of the elements, the optical system. That defines the smallest frequency you can see. It's referred to as the Nyquist limit. But if you have a signal that's faster than your limit, you're still sampling. And what occurs is, as shown in this slide, you have a signal that's a much higher frequency than what you're sampling at. And so you take it at the wrong spot and produce what you think is a lower frequency result. You're taking measurements of a high frequency signal, but it appears to be a low frequency signal. That's the aliasing problem that we run into. And you actually see that a lot. You'll notice in the lower right of this slide that you're looking at, this is a roof line with some tiles on it. And you can see these lines that occur across the image. That's the aliasing that occurs. Your camera is taking a picture at a lower frequency than the tiles that are on that roof, and so you get these fake lines because the aliasing problem makes it look like there's a lower frequency signal. So how do we deal with this problem? Well, as you can see here, we have the Nyquist limit of our signal, and we have an MTF to the left of the Nyquist limit. That's our measurement. All the frequencies at a higher rate, they produce a curve that's going to get actually mapped back onto the Nyquist, onto the MTF curve, so that all those images or those frequencies, they affect or impact our lower frequency measurement. The way we approach this problem is to try to increase the effective sample rate. We can't change the actual sample rate, the Nyquist limit, but we can sort of trick the system by sampling at a higher rate. And we do that again with our edge. Our edge is cutting across at different points on, or at every line of our sensor. And as you can see in this graph, because of that edge, that slanting edge, and the fact that we're crossing at different points, we sample at different points along the effective edge. The edge will take up more than one sensor element, and as we go down the line and keep shifting that edge that we're measuring due to the slant, we get more samples at different parts of that curve. Because we know where, and we can figure out where we're actually crossing on a sensor element, and we know then what the percentage is of the curve that we are getting from each line, we can interpolate or fit the results into each other, creating what looks like a more effectively sampled curve. We basically have multiple times our sample rate because we can take from different rows the actual sample rate and combine them with other rows. This effectively higher frequency sampling curve gives us a rate or a result that doesn't impact our Nyquist limit. That's still the limit of the system. But the sampling, the effective sampling limit, goes out much farther to the right. And you can see in this curve that we take that sampling limit, and now we've moved all the aliasing impact way far out to the right, much higher frequencies. And when that maps back into our lower frequency stuff that we're interested in, it is occurring down in the places where the result is around 1 anyway. That doesn't have a big impact on our final result. So by interpolating the slanted edge, we get an effectively higher rate that we're measuring, and we get a much nicer curve. And this next curve is actually coming from an interpolated result. This interpolation methodology, when everyone was experimenting with it initially, we all had different ways we tried to put it together. The ISO committee put together a standard. It's called the ISO 12233 standard to define how we are to go forward with this interpolation method. It's one of the few effective standards we have in this realm. So the MTF standard, ISO 12233 MTF methodology, is implemented in a way that we can go forward and all of us have the same method and the same result from the test. It's very important and a modern implementation of the MTF test. Okay, so I think that covers all the details. I think the last step is to talk about what are the uses of the MTF. Well, MTF is used to characterize the camera so that we can understand how effectively we can see certain or different sizes when we're looking at an object. And it allows us to detect for failures because we have some expectation of what the camera should do. If it doesn't meet those expectations, it's failed. It gives us feedback on focusing, and so that's an effective calibration step. We can look at an MTF, we can actually see an MTF occurring live, and as we adjust the focus, see it change, and we try to peak or get the best MTF we can out of the system, and that's our optimal focus. We can compare devices within a model series with that MTF to make sure we're manufacturing it properly. We can compare across cameras. We have to be a little bit careful about what we're looking at. And to also remember that even though something may have a higher MTF or a lower MTF at a particular spatial frequency, it all matters on what we're trying to do. right? If we are trying to get a big picture of an entire battlefield and we're looking for missile launches, that's very different than if I'm looking for a person that's coming at me to be able to identify if he's a friend or foe. So our MTF requirement varies depending on the task we're trying to accomplish. And as long as we are aware of that, then we can pick out the camera that has the MTF most appropriate for the task we're after. And that's MTF.